Hi, I'm Justin, and today I will be talking about the Passive Circuits Lab. So to begin with, we have a few equations that we want to look at. We have our Ohm's law equation, and we also have equations for finding the power through an element. So here we're saying a voltage drop is the current through something times its resistance. So it's important to remember that voltage is a potential, so you're always finding a potential difference. So this would be the voltage before the element minus the voltage after the element. So we're always, whenever you find voltage, you're actually finding V high minus V low. So you've got some difference between 2 points. So for power, we can either be finding the power for an entire circuit, which would be all the current drawn by that circuit multiplied by the voltage it takes to run it, or we can be finding power through a specific element if we know the resistance of that element, or if we know what the voltage drop of that element is and the amount of current flowing through it. So a voltage divider is one of the most basic circuits we can make, and it's useful for a lot of different things. So we have some input voltage, and we have two resistances that I'm going to call R1 and R2. So using Ohm's law, we can find the voltage drop across each of these resistances. So I'll call the voltage drop across the first resistor V1, and that is equal to I R1. And the voltage drop across the second resistor I'll call V2, and that will be I R2. So because there is only one loop in this circuit, all of the current has to pass through these resistors because it's just two resistors in series. So there's only one loop, so the current is the same between those two. And we see that the voltage drops are then directly just related to whatever the resistance is. So for the same amount of current, if your resistance goes up, you lose more voltage across it. If your resistance goes down, you would lose less voltage across it. For me, it's very helpful to think about electricity in terms of something that makes a little bit more physical sense to me, and for me, that correlation is with water. So if you think about voltage as being like your pressure, it's the potential that you're using to cause the flow. Your current is then like the volumetric flow rate. It's like the amount of water you get flowing or amount of fluid you have flowing. And your resistance is the resistance to that flow. So a large resistance would be like a very restrictive pipe, like a very small pipe. A small resistance would be like a very large pipe or a pipe with little resistance. So if you think about it, if you have for the same pressure drop, if you had a very large pipe, so a small resistance, you would get a lot of flow. For that very same pressure drop, if you had a very restrictive pipe or a large resistance, you would have less flowing through it. So for me, that's very helpful when trying to imagine what's going on in a circuit. So we've got a couple of things we can do with just this basic thing. So we know, because we have just this voltage source, so the potential here and here must be the same as the potential there and there. So we can say that VI is V1 plus V2 because these two voltage drops have to equal the input voltage. We can also say, since we just have two resistors in series, we can write this as an equivalent resistance, and I'm going to say that's R total for this. And because they're in series, that's just the two resistors added together. So if we want to find the current, we can rewrite our Ohm's law equation to be VI over the total resistance. And if we want to write these in terms of our individual elements, we can say that's V1 plus V2 over R1 plus R2. So this is going to be useful to find equations where we can find either a voltage drop or a resistance without actually needing to take the in-between step of calculating the current. So if we plug this in directly for our V2 equation here, we can say that V2, and I'm going to write this VI plus V2 as VI, is VI over R1 plus R2, and then, so that's the current, and then it's being multiplied by R2. So here, now we can find what the voltage drop across this element is if we know what our other resistor is, we know what our input voltage is, and we know what its resistance is. So this lets us skip that in-between step of finding the current. So this is a very useful equation for us. So we can do some things where we can rewrite this now, and we can also write an equation where we get R2 equals something. So if we know what our voltages are, we know what our other resistance is, we can find what the resistance of this element is. So let me show you that. So we can say V2 over V1 plus V2 is equal to R2 over R1 plus R2. So here all I've done is I've moved this over, and this is showing why we call it a voltage divider. So here we see the voltage drop across this element compared to the total voltage is the same as the ratio between that resistor and the overall resistance. So this proportion is always true. So we can write, going back to here, I'm going to multiply across I'm now going to bring this V2 term through. So I've got V2R1 plus V2R2 is VIR2. So now I'm going to bring this term over, so I have my R2 terms all on the same side. So that gives me V2R1 is VIR2 minus V2R2. So going from there, I can now combine these. So I can say V2R1 is R2 VI minus V2. So now if I just bring this term over, I've got an equation that is R2 equals something. And that is, so V2R1 over VI minus V2. So if I know what the voltage drop across the element is, I know what my input voltage is, and I know what the other resistor is, I can find the actual resistance of that element. And again, this is skipping the step of having to have your current, having to calculate it. Again, this is only for a basic voltage divider, so something with just two elements in it. So similar to this equation, or similar to this proportion that we found, we can write a similar one for resistance. So we can say R2 over the total resistance minus R2 is equal to V2 over the total input voltage minus V2. It was a very similar thing to this relationship we found. So the relationship between a resistance and the total resistance minus that resistance is the same as the relationship between the voltage drop across that element and the total voltage minus the voltage drop across it. But again, these two equations right here are going to be the most useful. So finding a voltage drop in terms of your two resistors and your input voltage, and finding a resistance in terms of a voltage drop, your other resistor, and your input voltage. Okay, so there's our basic voltage divider. Now, one of the things that we look at in this lab is something called circuit loading. So you load a circuit anytime you add another resistor in parallel. So we had our basic voltage divider with R1 and R2, but if we add another resistor in parallel with R2, we call that loading the circuit. So we've added an additional load. This power source now has to provide current to flow through. Given an additional path for current to flow, we've added another resistor. So anytime you add a resistor in parallel, you lower the overall resistance. And that may seem counterintuitive, but the reason for that, again, if we think about it in terms of water flow, so if you ever add another pipe in parallel with a pipe, you would let more water flow through because you're giving more paths for the water to flow. It's the same way with a resistor. Regardless of what that resistance is, this equivalent resistance will always be less than either of those by themselves. That's because we're giving additional paths for current to flow. So the voltage drop between there and there is the same for both of these resistors, but the current through them is different. So because we've added this extra current flow, and we've changed the equivalent resistance between this point and this point, we've changed what the voltage drop is compared to our basic voltage divider of just two resistors in series. So this voltage drop would be different than just the voltage drop across R2 without that resistor there. Now, how much that changes really depends on the magnitudes of these two resistors. So if R3 is much larger than R2, then this equivalent resistance is very, very close to R2. It will change. It'll always change if you add another resistor in, but it will be very close as long as R3 is much larger than R2. And that means that the voltage drop will be very similar to whatever it would have been for just R2. But if R3 is of a similar magnitude to R2 or is smaller, then this equivalent resistance of those two in parallel will be much different than just R2 by itself. And in that case, your voltage drop is going to be significantly different. So that's why circuit loading can be important, because knowing what this resistor is, we can significantly change what the voltage drop across that is. So one of the most common cases where you'll see a loaded circuit would be when you use a multimeter to measure a voltage drop across a resistor. So when you attach the two probes of your multimeter to measure that voltage drop, you would put one there and one there. You're really adding the multimeter in parallel. So that multimeter has some internal resistance, and you're really creating this circuit. When the circuit you want to measure is this, you end up making this circuit. So you've added a resistor in there. So just by trying to measure the voltage drop, you're going to introduce some error and change what that voltage drop across that element is. So one of the things we do in this lab is we calculate what the internal resistance of a multimeter is, and then we try to find what error is introduced for different values of R2 if we tried to measure that. Okay. Another thing we're going to look at in this lab is something called a thermistor. So a thermistor is a temperature sensor that is resistance based. So they're semiconductor materials. As their temperature changes, their resistance also changes. So by using a thermistor in a simple voltage divider, we can find what its resistance is, and from there we can find out what temperature it's at. So this would be an easy way to measure air temperature, or if you put it onto a thing, you can measure the temperature of some item by making your thermistor the same temperature as whatever that item is. So here we're going to use it as the second resistor in a basic voltage divider. So I have an R1 and then I'm calling this RT. And a lot of times you'll see this with an arrow through it, and that arrow just means that this resistance can change. So if we have it in a basic voltage divider, we can measure the voltage drop across this, and then we can use that voltage drop to find what the resistance is, and then we can use the resistance to find the temperature. So when you get a thermistor, the manufacturer will give you some properties of the thermistor as well as an equation to relate resistance to temperature. So for the resistor we'll be using in this lab, the equation that the manufacturer has given is this. And that's a minus T naught times T. So we have a couple of properties of the thermistor that will have to be given to you by the manufacturer. So that is R naught, T naught, and beta. So for the resistor that we are looking at, R naught is 10 kiloohms. T naught is 25 degrees C. So that is the resistance that the thermistor has when it is at 25 degrees C. So this is a reference resistance and a reference temperature. So when the thermistor is 25 degrees C, that is the resistance of it. Beta, this B value here, is another property. It's sort of like a scale. And for the thermistor we're looking at, it's 4073. And just be known that that is given in terms of Kelvin. So when you use T naught in this equation, you have to convert T naught to Kelvin. So another thing that the manufacturer will give you is a delta T value. So this is how much the thermistor heats up from the power being dissipated by it. So remember I gave you equations for power at the beginning of the lab. They are also in the manual. So if you know how much power is flowing through a thermistor, you can find out how much it heats up. using this delta T value that they give you. So anytime you put current through a resistive element, it heats up some. Some of that electrical energy is turned into heat in the material. So for the thermistor we're using, delta T is 2.5 milliwatts per degree C. So for every 2.5 milliwatts of power that flow through it, that thermistor heats up 1 degree. So this equation that they give us is resistance as a function of temperature. But for using this as a temperature sensor, it makes a lot more sense to have temperature as a function of resistance. So if we divide both sides by R naught, we get this. So we can then take the natural log of both sides. So we have the natural log RT over R naught is this beta multiplied by T naught minus T over T times T naught. So then I would divide both sides by beta. So we have 1 over beta, the natural log RT over R naught is T naught minus T over T times T naught. Now since we have multiplication in the denominator and addition in the numerator, we can split this into two separate things. So we can say that's T naught over T times T naught minus T over T times T naught. And then we can cancel these. So now we have 1 over T minus 1 over T naught on that side. So by adding the 1 over T naught over, we can get just temperature by itself. And since we want it to be equal to temperature and not 1 over temperature, we're going to take all of this side to the negative 1, and now we have an equation where we can find the temperature that a thermistor is at if we know what its resistance is. So in the lab you will have to take this another step further, and we will be asking you to give us an equation where you can find temperature if you know what the voltage drop across that thermistor is. Okay, so there's the basic stuff that we want to look at as far as the theory behind this lab. So I'm going to go through the lab a little bit and talk about some of the common questions that people have and sort of what we're expecting you to do. So we are giving you a template to answer these questions with. So you'll put your name, email, your lab section. We're going to want you to fill this out with your answers, convert it to a PDF, and then that's what you're going to be submitting on Canvas. So there are a few places where you would have measured things in the lab. We're going to be giving you those values that you would have measured. So for example, these voltage drops and voltage drops for the thermistor. We're going to want you to answer all of the questions from the lab. We've given you blanks for everything we'll be looking for. You'll fill out the tables from the manual. And again, you're going to convert this into a PDF. and that's what you'll be submitting. So make sure your answers are all there, because this is what we'll be checking. So as far as the lab goes, you've got your first section. We're using this figure. We want you to calculate what the voltage drop here is going to be, the current, the total power, so the whole power for the circuit, and then the power being dissipated by R1 and R2. And we've given you values. So here we're looking at how differences in the actual resistance and what the resistance is supposed to be for a resistor affects the voltage drop. So again, looking at this figure, we want to know how differences in these resistors from what they're supposed to be would affect that voltage drop. So next you'll be still using figure 2.2, and we're going to ask you to calculate V out for some different given inputs, and then also calculate what the current would be. Again, for these different resistances and different input voltages. So again, we've given you a table to fill out, and we've also given you what all these resistors are in that table and these input voltages. So next, we're going to be asking you to calculate again, but this time we're going to be using figure 2.3 here. We've given you values for R1, R2, R3, VI. We want to know what this V out is going to be. So now, still using figure 2.3 here, we've given you input voltage and a few different values for R1, R2, R3. And we want to know what V out would be. So we're going to be calculating these voltage drops here. So for this table, we're going to be using a basic voltage divider, but with a multimeter, with a digital multimeter, as the second resistor. So by using the voltage drop across the resistor, we can find what its resistance is, which is what we're going to be asking for here. So we're going to give you voltage drops. We're going to give you values for R1. We're going to give you input voltages. We want to know what the calculated resistance of that multimeter has to be. So then we're going to see what is the error introduced when we use this multimeter to measure the voltage drop across a resistor. So for this, we were thinking about our basic voltage divider here. So if we have some resistor here and we want to use our multimeter to measure the voltage drop across it, when we put the probes of the multimeter either side of this resistor to measure it, we actually create this circuit, with this R3 being the resistance of the multimeter. So for two different cases, for one where R2 is 10 kiloohms and R1 on R2 are 10 kiloohms, or one case where R1 and R2 are 10 megaohms, we want to know what the percent error is. So the expected voltage minus what you would actually measure over the expected voltage. So again, your expected would be this circuit, and what you would actually measure would be this circuit, figure 2.3. So then you're going to have to give us that equation for temperature for a thermistor as a function of the voltage drop across it. So I've given you already temperature as a function of this resistance. Now we want you to show us what the equation is that's temperature as a function of the voltage drop across that resistor. So then the last section here, we're going to give you input voltages. We're also going to give you what the voltage drop across the thermistor was. And using this equation that you've come up with, we want you to tell us what the temperature that the thermistor is at, how much power it's being dissipated, and then using the power, how much did it heat up. So you can ignore this last question. We are not asking you to do that. There's not a space for it on the template. Everything else there is an answer for. There is a spot to answer. If you have any questions about what you need to do for any of this, send an email to one of the TAs. We'll be happy to help you. And again, you'll have a week to do this lab. It should only take you a couple of hours, especially, at worst, especially since you don't actually have to make any of these circuits. We're just asking you to do some calculations. So make sure you use this template. Make sure you fill it out completely. Make sure you convert it to a PDF before you submit it. The only other thing is we ask you for a graph when you come up with this equation. We also want a plot of temperature and V out. So temperature on your vertical axis, we want you to plot this. We give you a range of temperatures that we want it over. So we want to see a plot of how temperature is affected by the voltage drop here. So T versus V out. Temperature as a function of V out. I suggest making that in Excel or something like that. You can do it in MATLAB if you want to. So make your plot, label everything, give me units, and then I want a picture of that, and you'll upload it with the template. So you can upload multiple files. So one will be the PDF, the other will be the picture of your generated graph. Okay, that's all I have for this week. Hopefully this is all fairly straightforward and should be pretty easy to do. Again, if you have any questions, send an email. Otherwise, I will see you next week.